Polytetrafluoroethylene is formed from the monomer tetrafluoroethylene, which is an odorless and colourless gas that is created by heating chlorodifluoromethane in between 600 and 700 degrees Celsius. These tetrafluoroethylene monomers are emulsified or suspended in water. They are then polymerized under high pressures alongside free radical indicators, which are ions or atoms that have single unpaired electrons, making it extremely unstable. This free radical wants to form a bond, so it attacks the double bond found in tetrafluoroethylene. However, there is now a free electron on the end of this chain that has started to be formed, which is known as polytetrafluoroethylene. So, another tetrafluoroethylene molecule has to come in. And the free radical acts on that and breaks out that bond. And it allows it to attach onto this chain. The polymer chain is composed of carbon atoms bonded to two fluorine atoms. The fluorine atoms surround the carbons and act as a protective casing. This allows the molecule to be relatively dense and chemically inert, as well as having a strong carbon-fluorine bond. The properties of polytetrafluoroethylene include a high melting point of around 327 degrees Celsius, being highly insoluble in most chemicals and solvents, having high thermal stability, high electrical and water resistance, as well as having a high flexural strength. These properties are due to the polar carbon-fluorine bonds and the dipole-dipole interaction that can be seen in between the polymer chains, allowing it to be tough and strong. Polytetrafluoroethylene will not allow alcohols, water, and other highly polar molecules to absorb onto or adhere to it due to the high electronegativity of the fluorine and the size of and number of electrons in the polymer's orbital. This results in the high electronegativity of the overall polymer structure, and thus explains why polytetrafluoroethylene is hydrophobic. Polytetrafluoroethylene has good dielectric properties and is an ideal insulator due to the strength of the fluorine-carbon bonds, the rigid structure, and the minimum movement of the electrons in the polymer. Polytetrafluoroethylene is chemically inert, which means that nothing will react to it due to the strength of the bond between the fluorine and carbon atoms. The most common use for polytetrafluoroethylene is the Teflon non-stick coatings in pans. However, it also can be used as a treatment for carpet and fabric to make it stain resistant, or as electrical insulation under high temperature conditions. Fluorine is extremely electronegative, however holds onto the electrons tightly and is satisfied with the overall polymer chain. The electrons will repel almost any other molecules that try to come close to it, preferring their own kind. They are unavailable for reactions that allow things to stick to each other or even cause friction, explaining why polytetrafluoroethylene is most commonly used as non-stick coatings on fry pans and as stain resistance on fabric and carpets. High thermal stability is due to the interlocking of the fluorine atoms, as well as the more stable and stronger carbon-fluorine bonds, which is why polytetrafluoroethylene makes for a good electrical insulator. Polyvinyl chloride is formed from the monomer vinyl chloride. The polymerization of vinyl chloride monomer occurs in an autoclave, which is a bit like a pressure cooker. The autoclave is filled with water and additives for the reaction. The autoclave is then heated, and the vinyl chloride reacts with a free radical in the same way that the tetrafluoroethylene reacted with the free radical to form polytetrafluoroethylene. This reaction of the free radical, polyvinyl chloride, will form. This then forms the polymer polyvinyl chloride. After a fixed amount of time, the reaction is ceased and the contents inside the autoclave are sent to a stripper, which separates the unreacted vinyl chloride from the polymer to be sent away for purification and reuse. The polymer is then dried, firstly in a centrifuge, then in a hot air dryer. This dry polyvinyl chloride is then passed through a sieve to be smoothed out into a fine, even consistency. In spite of its amorphous qualities, PVC is hard and rigid due to the strength of the intermolecular forces. Due to the strength of the carbon chloride bonds and overall bonding structure, polyvinyl chloride is relatively thermoplastic, allowing it to be easily melted and molded into many different shapes. The chlorine atom, which is bound to every other carbon chain, contributes to the high durability of polyvinyl chloride due to its high resistance to oxidative reactions, allowing for original molded shapes to be maintained even through many significant pressures over sustained periods of time. Polyvinyl chloride has a high flame resistance due to the fact that when an attempted combustion is performed, the chlorine atoms that are released inhibit the combustion from occurring. Polyvinyl chloride is the most widely used and cheapest polymer after polyethylene. Its most known use would be in PVC piping, which is used as sewage and drainage pipes. However, it is also used in hoses, in guttering and drainage in homes, and electrical insulation. Polyvinyl chloride is resistant to both water and fire. This is due to the chlorine that is found in the polymer. This allows it to be used in the production of raincoats, shower curtains, and the PVC piping, as well as electrical insulation and sheathing on cables to prevent potential electrical accidents. The polar chlorine groups of the polyvinyl chloride, as well as the amorphous qualities, allows for it to mix well with other substances. This allows for easy colouring, printing, and adhesion. This is why PVC is commonly used in different signages. Plasticers can be added to the polyvinyl chloride to enhance its properties and make it more flexible, allowing for versatility.